All right, so this is the fourth lecture from Chapter 8, and you should have just finished watching that short video on the electron wave model. And so now these pictures hopefully make a little bit more sense. So in this one, the electron waves are in those, it's like the model for the standing waves. So you can see the little up and down, the spaces where they're constructively interfering with each other, the area right here, the nodes where they would be destructively interfering with each other. So this is what those electrons would look like if they were actually in one of those levels, N1, N2, N3. This is what it looks like when the wavelengths would be overlapping each other. So this would be when they would be in between one of those levels, and you can see there's no standing wave. So they are interfering too much and canceling each other out. So that means that we had to have then a new model. We still draw the Bohr model, and you'll see that in another slide, because it's easier to draw than this shell model. So the shell model is what you see here. What the shell model did is it took the Bohr model, but then includes the wave nature of electrons, which basically means it put them in 3D, because the Bohr model really was kind of looking at it in that 2D kind of structure, and the shell model is looking at it in this 3D more structure. So the shell, each shell is just the region of space around the nucleus where the electrons reside. We now know that the electrons don't travel just like a planet around the nucleus. We know that they can travel in any direction 3D in that shell as long as they are still in that standing wave. Then if they get that energy, they get hit by a photon or so forth, then they can jump up to another level, and then they'll jump back down as they lose that energy. So as you can see, the shells are concentric, so they are packed inside of each other, kind of like one of those little Russian dolls. And we know there are at least 7 shells. There may be more. If there are more, it's going to be from man-made elements, not from natural elements. The natural elements are limited to 7 shells. And each shell can only hold a specific number of electrons. So you can see those little numbers up there at the top. Let's take a look at them in a little clearer detail. So here you can see the different models. So there's the shell model. This is kind of a cloud model. And here is our Bohr model. So you can see why this one's a little easier to work with. But now you can see those numbers much more clearly. So shell 1 can hold a maximum of 2 electrons, no more. So it will fit just 2, and then anybody else has got to go to the next shell out. So shells 2 and 3, you can see it's shells 2 and 3, the next 2 rings out, or the next 2 shells out. Those can hold 8 electrons each. Shells 4 and 5 are, and I know this sounds weird, it's not 16, it's 18. So it's not an easy one to remember, because everybody wants to always say it's 16. But it's actually 18 electrons for each of the next 2 shells, for 4 and 5. And then shells 6 and 7 can hold 32 electrons at the maximum. So we've got 2, 8, 8, 18, 18, 32, 32. So once you get out to this last shell, shell 7, you're talking about a fairly large atom, because the electrons are pretty far away from that nucleus. All right, so with all that, now we're going to take a look at the periodic table, because we've got a good background on looking at it. So it does contain the information on the known elements. Like I said, we're pretty sure there are some unknown elements, and we are actually working to make some of those. Some of them are likely going to be made in things like CERN, where they are smashing atoms. And we know some of them have previously been made in things like nuclear reactors. So things that you can find on most periodic tables, you're going to find the atomic mass. You're going to find the atomic symbol, that's that shorthand like carbon, C, for the element. The atomic number, Those three items are always going to be found on a periodic table. There may be other information that's going to be on that periodic table. So if we take a look at ours, you'll see that there's a lot of information here, and we'll take a look at it in more detail in a minute. But you can see at a minimum, we've got that symbol, we've got the atomic number, the smaller number, the atomic mass, the larger number, that's usually that decimal point. On our table, we've actually got the names of the elements, and then you'll see these little 3D 4S numbers. You don't need to worry about those, but if you are taking a higher chemistry course, those actually are describing electron configurations, so those can be really helpful for that kind of sort of thing. All right. The thing is that a lot of people don't realize that the periodic table is actually organized in a very specific way, and so that's one of the things we're going to take a look at. Now, it may not have noticed, but most of the elements are one group or one type of material. So let's take a look at periodic table. So this is similar to the one that I just had up, but you can see it had a little less information put onto it. So here we just have the symbols and the atomic numbers, but for what we're looking at, that's all we need. So if you take a look here at this table, do you notice what most of the elements are? And this one's helpful because this one's color coded. You should notice that most of the elements are metals. In fact, very few of the elements are nonmetals, these pink ones over here. Now you may notice some pretty well-known ones: carbon, nitrogen, oxygen, phosphorus, sulfur, chlorine, iodine. So some really helpful and necessary elements on the non-metal side, but a majority of our elements are metallic. So let's talk a little bit about these metals. So we've seen these guys before when we've talked about different properties. So we know that these are good conductors of both heat and electricity, as we found out. These guys are going to be opaque, meaning you can't see through them, and most of them are shiny. There are a few exceptions. Things like lead aren't particularly shiny, but a majority of the metals are going to be shiny, and that is comes from that reflective property of them that we saw in the light chapter. They all have the property of being malleable. What that means is that we can hammer them into new shapes without breaking them. And so probably familiar with the thing of like blacksmiths making, tools, or, us forging things into knives and so forth. We can take these metals and make them into new shapes without damaging them. There's also the property of being ductile. What ductile means is that we can take these metals and we can draw them into wires. Again, it's a property related to being malleable, but we can draw them into fairly thin wires. Think about if you've ever seen copper wire, especially if you've ever broken like a telephone cord or a power cord. If you've ever seen the inside, those are extremely thin wires, and so they've been able to be drawn into those very thin wires, and they're still, even though we may be able to break them, they're still pretty strong compared to other materials. These are solid at room temperature, with a few exceptions. These four metals are not going to be solid at room temperature. You may recognize one of them. My guess is that you probably don't. You probably recognize mercury. A lot of people are familiar with mercury. It used to be in thermometers. You generally will not find it in thermometers now. Thermometers generally, if they're not electronic, are going to be filled with alcohol. It's going to have that red liquid in it. And that's what these guys are. Mercury, gallium, cesium, and francium are going to be liquid at room temperature. Now, gallium will be solid just at room temperature, but just a little bit of heat, like the touch of your hand will turn it into a liquid. So if you've heard of like the disappearing spoon, that's usually built out of gallium because of that very, very small difference in temperature, turning it from a solid to a liquid. Now, you may have noticed that helium, or I'm sorry, not helium, hydrogen is kind of marked as a metal. And it is a metal, but only under extremely high pressure. So most of the time, hydrogen is going to act as a nonmetal or a gas, but under very, very high pressures, it will turn metallic. So on the other hand, we've got nonmetallic elements. So did you notice which side of the periodic table that these guys are on? If not, take a look at your periodic table because they are labeled just like the one we saw. These are going to be poor conductors of electricity and heat. They are opposite of the metals in almost every way. They may be transparent because a lot of them are actually not solids. They are not malleable or ductile. So of the ones that are non-metallic that are solids, if you hit them with a hammer, they will break. So things like sulfur and phosphorus, they will actually just crumble if you try to hit them with a hammer. So they will shatter. At room temperature, they can be solid, liquid, or gas. So let's take a look at these guys, the non-metal elements, to see who is a solid, who is a liquid, and who is a gas. So we're looking at the green elements over here. So all of the elements that are way over in the corner here, or in the last row, are all going to be gases. The nice thing about this periodic table is if you have it here in color, they're actually color-coded. That's part of why I love this table. So if you look here, it's got physical states at 25 degrees. That's basically room temperature. If it's red, it's a gas. If it's blue, it's going to be liquid. And if it's black, it's going to be a solid. So you can see that a good number of the nonmetals are going to be gas at room temperature. There are some solids, so carbon, phosphorus, sulfur, and selenium, as well as iodine and astatine. They're all going to be solids. There is one liquid, and that is bromine. So we do have the whole variety of nonmetals. And again, all of these guys up here, for the most part, are going to be transparent because they're all gases. The other guys are going to be mostly opaque. Some of the liquid versions, like you can get liquid iodine, that's a compound usually. It might be transparent, but mostly it's not. It's going to be opaque. All right, one last group to talk about, and that is the semiconductors. These guys are also sometimes known as the metalloids because they fall in between the metals and the nonmetals. So if we go back to our periodic table and take a look, these are these elements here, and I just noticed that there are actually 7 of them on your periodic table. One of those should not be marked, and I can't tell off the top of my head which one it is. But these guys that run this stair step down the center of the periodic table are going to be the nonmetals or the metalloids. And these guys have a combination of features between the two. They are going to be brittle and non-malleable. So they will be like a nonmetal in that way, but they are weak electrical conductors. So that's why some of these are going to be used for different types of electrical uses. The best known one is silicon, and that one is used in computer circuit chips because it will conduct electricity, but not super well, and it will change that conductivity when it's exposed to different temperatures. All right, so we're going to stop here and pick up with the patterns in the periodic table in our next lecture.